So in the previous video, we discussed in detail about the state search spaces. So we are into a main subject of problem solving, where we taken like two dimension of problem solving. One is a knowledge, and another is using search. So I have explained that in the previous video. If you missed that, you can watch that and you can follow these things. So here we are going to see the basic searching algorithm. So we'll go directly. So there are n number of problems to us. We have many problems. I have discussed. I put like basic three problems in front of you. One is a 8 square problem that we discussed in the previous session, and another you can see there is a river crossing problem, and another is a Rubik cube problem. In that way, like you can take chess or TikTok or any other game. So we have many games, and like every game can be considered as a problem, and we need to solve that problem. So how we are going to solve the problem? Like we cannot have a different program for solving this issue. We should have some standardized method to solve the problem. So what we are going to do is like we are going to put a standard algorithm to all the problem in such a way that the problem is getting solved. So I'm going to use some basic methodology for this searching technique. So this algorithm, this searching algorithm that we are going to devise now is going to be a basic algorithm from which we are going to generate the other standard algorithm which is present right now, the biggest algorithms like VFS, DFS, genetic algorithm, and whatever the thing that is to be followed is going to be a basic from this thing. So this algorithm is going to be a scratch algorithm, that we can say it like that. So here I'm going to use one methodology like generate and test. So generate means nothing but like we are going to move from one state to another state, that we can say as a generate methodology. And test is like whether the node that we are going to that has been generated has been reaching the goal state or not. If you look at the previous session that we discussed, there we generated many neighboring nodes from a single node. So that is possible, like, and we check that that single node that we have generated is reached goal state or not in that way. So here I'm going to have two functions. One is a moveGen function and the goal test function. moveGen function is going to generate neighboring node from that initial node, and the goal test is going to check whether that node has been the generated node has reached the goal or not in that way. So like this thing, like basic concept, like you'll be given a starting state and you have to reach a goal state. Supposingly, say I told the example in the previous session, like you'll have a starting state as Chennai and you need to reach Delhi, that will be the goal state. You'll be having the neighboring node from Chennai, you need to go to Bangalore, then to Mumbai, in that way. So each and everything we can, like Bangalore is a neighboring node and Mumbai is a neighboring node, and then you'll be reaching Rajasthan, like that. It will be to reach Delhi, what is the node that we are going to travel. So that is the thing that we are going to see in detail now. So these neighboring nodes are generated by the moveGen function. We'll see in detail like how we are going to use this. So earlier we discussed about this problem, 8 square problem, and we know how the neighboring nodes are generated. The initial state is like we told us yes, and the goal state is like we need to reach this goal state. So how? So this problem is clearly explained in the previous session. You can watch there. Here, like how we are going to represent this in the computer. See, we are going to devise an algorithm, but before devising the algorithm, we need to be pretty much sure that like how we are going to put this into a data structure, so that we can apply our algorithm in this. So like initial stage, we taken as a node. Since we are talking about node, this concept is like we are devising a graph. So graph, the entire graph, and in the graph, like from one node we are generating the other nodes, so the nodes will be linked, and we need to find a path in such a way that we are reaching the goal state. So that is what we are going to show. So the basic structure, like we are here like we are going to deal or take is list. We can generate a list, like we can put a list and we can add this element. See, S is an element, G is an element. In that way we can add those elements into the list and we are going to check one by one. So the basic structure that we are going to take is a list. So initial step is like we are going to add this initial S value. That is the starting point of our problem where we are left, like we are in a Chennai. That is the starting point of our problem, that we are going to put that into a list. I'm going to create an open list where I'm going to add this S element into the open list. So that is what I done here. That will be the initial step of this algorithm. So next is like I'm going to check whether this S have reached goal state or not. Why I'm going to check? Supposingly say like we are in Delhi and the problem that is given is telling that we want to reach Delhi. What will be the scenario? We can put it in other words. Like for example, I've given a problem to solve a Rubik cubes that we have discussed in the previous session. So what if like you are given with the solved Rubik cubes? We need not put in any other steps. Since it is already in a solved state, we need not go for any other steps. So what is the initial procedure is we are going to check that S with the goal state. And we are going to say that if S is a goal state, then the problem is solved. But look at this problem here in front of us, that here the S is different from G. So it will be returning false. So in the previous scenario, like I used here I'm using this goal test function to check S with G. If it is same, I'm going to return true, or else I'm going to return false. So what if S fails? If S is failing, I'm going to put another function which is moveGen function, where I'm going to generate A, B and C. What is this A and B and C is like the neighboring states of S. How this neighboring states of S is generated? See, for example, this is a 8 square problem. Here you can see there is a space in between 3, 6 and 1. So what are the other possibility? There will be 3 possibilities from this thing. One is a A state where I have taken that 1 up. So the space where 1 is there is left. And you can see the B state where I have brought down 3. So the space in the 3 will be left. So in the third one, like in C, you can see that 6 is pushed left side. So in the middle column is left out. So these are the possible neighboring state that I am generating using the function moveGen. So I have discussed two functions. One is a goal test function, which is going to check whether I have reached a goal or not. And the another is a moveGen function, which is going to generate the neighboring node for me. So here in our scenario, from S we can reach all these 3 possibility, no other possibilities. From this, actually I should reach A or B or C. So this can be related with any other ratios. For example, I can say if I am going to travel from Chennai to Delhi, I will have n number of steps. Like S is having 3 steps, I will have n number of possibilities to reach Delhi. So that all this n number of possibility, I can say it as a neighboring node. So those neighboring nodes are generated using this moveGen function. So I think it is clear. So I have drawn this in a graph. For example, S will be the starting node, and from there I am going to move towards A, B or C. So these are the possible neighboring node that I have generated. This is a form of graph representation. So I have added this all things into open list. So here you have to think one thing, like I am moving from S to A, B, C because I have tested S with the goal state and I have failed. Since I have failed, see, S is not equal to G. Only then I am generating this neighboring node A, B and C. So what I am going to do is I have a list which I told you, like open list, where I have added that S and I fetched that S and I have checked with that algorithm, goal test algorithm, and it fails, which means that I cannot, like, S is failed. So I need not check again and again the value of S. What I can do is I can remove the S from the open list, and I'm going to add the successor of S, which is like A, B, C, as we discussed so far, into the open list. So the open list will contain this element A, B, C. It will remove the S element. Now what I'm going to do is I'm going to fetch this A. I'm since yes is failed, I'm going to fetch A, B, C, which is like in the open list. I'm going to fetch one by one, and I'm going to check that A with the goal test. If A is pretend to be the goal, then I will stop that algorithm there and I will print I have reached the goal. If it is not the goal state, then I am going to continue with B by leaving out A. Before leaving the A, what I have to do, I have to add the child of A, that is the successor of A, that is a neighbor of A, into the open list. So the list will contain all the element, the successor of this element which has been removed. So that my test will also be continued until I reach the goal state. So this is the first algorithm that I am going to implement. So like this, my node will be going on. You can see in this diagram, from yes, I travel to A, B, C. I will choose A. If I go to, I can go to D or E. If I choose B, I can go to F or H. If I choose C, I have 4 options. This way, it will continue until I reach the goal state. So my algorithm is devised like this. You can see that I have moved that yes into open list. I'm going to pick one node from the open list. So any node from the open list, I've left out that open list. You can put open of in there. So I'm going to pick any node, say n from the open list, and I'm going to test. Like with the picked node, I'm going to test goal test. If it is not true, I'm going to remove that node from the open list. That is what we have mentioned. And the open list is going to add some element which is going to be a successor of the node n. So as we discussed, this algorithm will be very, very simple. So I have written each and every point whichever in the first slide to the till now that we have seen as an algorithm. I think it is easy to follow. If you have doubts, you just put a comments there. So this is the first algorithm we have devised. So next scenario is I'm going to like go for some better algorithm than this. So how we can reach the other algorithm is like criticizing the first algorithm. So how we can criticize is, see in this diagram, it is a maze problem where we have to reach from one path to another path. How we are going to reach? We should reach in such a way that we should not be in a loop. For example, in a maze problem, you know what is a maze? You should not revolve around the same path again and again. If you are revolving in the same path, what will happen? You will not reach the goal state. How we can solve this issue? That we can see in the next session. With this, I finish this first simple algorithm, and we'll go for that next simple searching algorithm, and then we'll go for BFS, DFS, and that uninformed search, informed search, adversarial search. In that way, we can go. So this algorithm will be the base for everything. I hope you understand everything. Thank you.